Joining me today is Oliver Tweedy from Sky, Director of Data Engineering. And today we're going to be talking through real-time streaming analytics with Dataflow, common use cases, and patterns. But before we dive straight into patterns, it's important to understand streaming and why it matters, and a couple of things that the Apache Beam SDK and Dataflow do to solve some of the common problems that you may run into. So we can have data that we're processing, and that data can be big. For instance, we could be processing from gigabytes to terabytes. It could be really, really big. So we may have huge amounts of data that we want to process every day and multiple days that we want to process. And that data can also be infinitely big. So we may have streaming data that's constantly coming. It never stops. And this gives a problem with processing, especially with unknown delays. So one of the more difficult things with unbounded data is unknown delays. So assuming that every record has an event timestamp, hopefully we would see the record show up shortly after the event that occurred. So if we look over here, the red record here, it happened at 8 a.m., and it showed up in the system shortly after. The yellow record happened at 8 a.m. and showed up in the system slightly delayed. But then we have this green record over here that has an event timestamp of 8 a.m., but showed up at 2:30, which is about a 6-hour delay. And there's several reasons why these delays may happen. The most common case is actually mobile devices. So with mobile devices, you can imagine that you get on a plane, you turn your phone onto airplane mode, you play a game on your mobile device the entire plane ride. When you get off, you turn your airplane mode off, and all those events shoot up to the cloud. And so you get all these events into your data pipeline all at once, because we had no connectivity during that period. Now, if we were doing element-wise transforms, such as just filtering out for the yellow records here, that's relatively simple. We don't care about processing time or event time. It's easy because it's a continuous transform. But when we get to grouping data via processing time windows, so let's say we want to do an aggregation. We want to count the number of events that happened per user. For batch, it's easy because it's bounded. We just read the input stream, and then as soon as there's no more data, we stop processing and we calculate the result and emit it. For streaming, we can't do that. You never run out of data, so there's no way of saying, like, this is the time where I output the count that I've seen. So most commonly, what people want to do is group data into processing time windows, or windows rather, and divide data up into small chunks so that they can compute aggregations over that chunk of time and then output results. So initial approach is to use processing time windows. Essentially, when a job sees a record, it looks at the wall clock, does that for a minute, and then outputs a record. But what we really may want to do is actually group that by event time. So instead of viewing something as time on the wall clock, viewing data as a stream, and group by our event timestamps within our data and output them as we see them. This allows us to perform calculations over the event time interval which the events have occurred. So essentially what we do is we take the input, which is all the events occurring in processing time, we regroup them and shuffle them to group them into event time and calculate meaningful analytics over our data. So I mentioned windows. What is a window? A window is just a function to divide data into chunks. Within the Apache Beam SDK and Dataflow, we provide several different window types to slice and dice your data in different ways. So for instance, here's some of the more common ones, fixed windows and sliding windows. So a fixed window, you could think of it as processing data from like 1 to 2, 2 to 3, so on and so forth. And so you're pretty much dividing up your data into time chunks and then grouping it and providing some aggregation on that data. Sliding windows, you can think of those as overlapping fixed windows. So an event that happened may actually end up in multiple different windows. So say that I had a sliding window that was an hour and it slides every minute. I essentially have windows that end up being 12:01 to 1:01, 102 or 1202 to 102, so on and so forth. And so I could have a lot of overlapping windows. And this is useful when you're doing things like analysis on maybe the input rate of the data, or calculating how many events that I've seen in the past minute or 10 minutes for a particular event type. In Beam, we also support data-dependent windows. So what if I wanted to group by something that was in my, my event itself? So I want to create windows for users, for instance. This is what we would call sessions. So every key here ends up in a different window. Sessions are defined by whenever there's a burst of activity. I want to group that into a window for processing and calculate statistics over that. And then when there's no data for a period of time, such as a gap, I'm going to close that window and fire it off. This is a common thing you may want to do in analytics, and it's supported out of the box in Dataflow and Apache Beam. So I've talked a little bit about the windowing semantics and how we would divide our data up and maybe do computations over it within a real-time analytics pipeline. But when does the answer come out? This is problematic because you have to know when to emit the result for the data that you're seeing for that window. By default, what we have is something called a watermark. The watermark tries to know when we are done with data for a window. So if the watermark says 12 o'clock, it means, to the best of our knowledge, there's no more data left before 12 o'clock. And we can calculate the result and emit it downstream. For external sources, it has to be somewhat heuristic. So for instance, for PubSub, we can actually do a read ahead of the PubSub buffer to essentially look at, is there any more messages left before a certain period of time? And then know that we can effectively emit the results. Now, going back to the mobile phone on a plane example, you could have someone who has data from 11 o'clock on their phone. They don't have any internet connectivity. And obviously, we can't know about that. So that actually becomes late data. So if we look at the heuristic watermark here, essentially you can see that while it does pretty well, it doesn't catch the 9 that happens a lot later than we expected. For the perfect watermark, it is perfect. It knows about everything, including events that may happen in the future. So what happens when you have late data? In the Beam SDK, we have a way of saying that I want to process late data. You can add triggering to your windows to indicate you want to process that late data. And there's several different ways of processing it. So for instance, using accumulating processing means that if I have late data show up, I want to add that late data to my previous aggregation. So for instance, if I was counting elements and I had a count of 50 before, and that late data shows up, I fire off that late data, and I give back a result of 52 instead of the original 50 when 2 late elements show up. I can also say I want to discard late data, or discard fired panes, rather. So essentially, if I wanted to do this count and compute the sum, I could have 50 elements that show up on time. I could have 2 elements that show up late. And as opposed to recalculating the result and firing off 52, I may say, forget about the 50 that I had previously calculated. I only want to get the count of 2 and discard those previous fired panes. So in this other animation, you can actually see some of our speculative and late firings. So in this case, the heuristic watermark is actually firing speculatively for records that show up before the watermark, and then also catching those late records for a given period of time. So we're actually able to capture a lot of that data that does not show up when we would expect it. So that was a little bit about streaming and sort of the common challenges and how Dataflow and the Apache Beam SDK helps address some of those challenges. For the subsequent section, we're actually going to talk about building a pipeline using some common patterns. So from simple element-wise transforms to grouping aggregations and that type of stuff. For this, we're actually going to use the scenario that I've been alluding to previously of capturing events and analyzing them for a mobile game. So let's imagine we have a mobile game, and we want to build a real-time analytics pipeline to analyze those game events that may be happening. And we want our game to be popular, too. So we want to be able to handle these events at scale and be able to do interesting things like compute aggregations over how many events that we're seeing per user or analyze the user behavior within the game app. We'll start out with exactly once processing. So starting to build this pipeline from the most simple case, we may have our gaming devices publishing up data into PubSub, then Dataflow processing that data, and then BigQuery finally landing that data into our data warehouse. We're using PubSub because it's a reliable, globally available message delivery service, and we expect our game to be popular worldwide, so why not? Now, if we're analyzing user behavior, duplicates which may enter our system may throw off our analytics. Right? So if I'm calculating counts, if I'm doing averages, if I allow duplicates into my system, I'm going to throw off the analytics that I'm doing and thus make them substantially less valuable. And this is also critical in other industries, such as retail or finance. So imagine I have a POS system which is generating transaction events. I obviously wouldn't want to double count those transactions. And same thing with trades or holdings. In this example, zooming in onto Cloud PubSub, you may think that it may cause a problem because it has at least once delivery semantics. So inherently, by using PubSub, we may receive duplicates within our system. Here, the colors indicate unique keys for the records. So we have red, yellow, green coming in, and we may have duplicate records that come out. However, when combining PubSub with Dataflow, we're actually able to achieve this exactly once semantics within our pipeline. And it's with relatively little effort. So if we were to zoom in a little bit on the records coming into our pipeline, they may look like this. We have attributes and a payload that comprises the message that's going into PubSub. Attributes are key value pairs. You can think of it as a header on the message. It allows you to sort of inspect the message and maybe route it in different ways or perform other operations without having to actually deserialize the payload. And the payload contains the serialized payload of our message. In this case, we're publishing JSON events up into our PubSub topic. And you'll see that we have a unique identifier within the message payload in event ID. So the first step to actually processing this in exactly once fashion is that we'll promote this event ID into our attributes. And this allows us to instruct Dataflow to direct to it within our pipeline and start deduplicating these messages. So we take a look at our example pipeline here for our game events. It may look like the following. So essentially, we have a PubSub IO transform. It's reading some data from a subscription, and then it's passing down data downstream to our transforms. So the first step was to add in that event ID into our attributes. Now we need to instruct Dataflow to react to that event ID. And that's relatively simple here, as opposed to just having a very vanilla transform with just specifying the subscription. We add in this .withID attribute. And this allows Dataflow to know, I'm going to look at this event ID and deduplicate on that as messages come into the pipeline. Now, this will deduplicate messages that are being caused by PubSub. So any messages that are duplicated as part of PubSub's at least once delivery semantics will be deduplicated automatically within the pipeline. There's also other areas in which we could receive duplicate messages, such as a publisher maybe publishing a message twice. This will also pick that up as well, but it will only do that within a 10-minute window. So we don't keep around the event ID deduplication table for past 10 minutes. So if you had a publisher maybe going, publishing a message at minute 1, and then they publish the same duplicate message at hour 1, minute 1, you would then have to account for that elsewhere in your pipeline, such as using a unique transform. So we're achieving exactly once semantics within our pipeline. The next thing we may want to do is think about how we deal with bad data. In order to deal with bad data coming into our system, we're actually going to add some things to our architecture, such as PubSub to handle as a dead letter topic, and Cloud Functions then to alert on messages which end up in that dead letter topic. So what does this look like in actuality? So we have this message being published in. You can notice that this message is malformed in some way. We don't have a closing tag on our JSON object. The event ID is no longer in the proper format. So we were expecting a string, and now it doesn't have the quotes around it. So by default, if this was to enter our pipeline, it's going to fail when we try to parse these messages, right? In Dataflow, we'll actually try to reprocess those messages forever in streaming mode, because we don't want to lose that data. So if that data fails and it throws an exception, right, we don't want to just drop it on the floor. So we'll continue to reprocess it forever, or until you tell us what to do with it, such as updating your pipeline or creating a new path within your pipeline to deal with the bad data. So what do? We can actually edit our ParDo function. So each one of those boxes is a ParDo function. Essentially, you could think of a ParDo function as almost like a map in MapReduce. ParDo function has a process element method, where it performs the computation. And so as opposed to just performing our computation and outputting records, what we'll do is we'll wrap it in a try-catch block, and then we'll output failed records for any exception to our dead letter tag. And that dead letter tag allows us to then retrieve those messages later on in our pipeline and then do something with them, such as output them to a persistent store. So if we were to go back to our pipeline here, in this case, we are now redirecting our messages to a different location. We're taking that dead letter tag, and we are then routing it to both BigQuery and PubSub. We're routing to BigQuery and PubSub because we want our support team to be able to analyze those bad data, to be able to inspect it within BigQuery. And then we also want to output it to PubSub for ease of reprocessing and alerting within our Cloud function. And so in this example, this is an example of a BigQuery table that you may see for dead letter processing, where we're storing maybe the event timestamp, the payload in bytes, and maybe try to convert the payload to a string to show more data about that payload so someone has more context, store the attributes and the error message and the stack trace. And this way, someone can go in there, see what the problem is, and then hopefully rectify it. So we've added handling for bad data within our pipeline, but we also may actually have another case which may cause failures. And that is schema changes. So for a mobile game, imagine that we have partners that are publishing this data. So our partners are publishing this data, and they may want to update the schema at some point. And we need to react to that within our pipeline. So we may need to add additional fields within our pipeline dynamically. Now, we could do this not dynamically. We could have coordination, like we could call up the partner and say, we're going to coordinate a release on this date, and have a lot of operational overhead. But we actually want to dynamically handle this, because then we're free from that operational overhead of having to manage it. So looking back at our messages, we may have the message on the left, which is the yellow message, which is coming in just as we expected in the schema that we expected. But we also may have a message on the right with like the green message here that has an additional field. So the partner may have added like a device IP or some contextual information that's useful for them, and we want to capture that. But if they added an additional field, we may fail on our insert into BigQuery. So we're going to have to account for that within our pipeline. So there's a couple things that BigQuery and Dataflow, or a couple of features of BigQuery and Dataflow that allow us to do this fairly efficiently. BigQuery allows for schema changes which are additive within the same table. So schema changes happen online and require no downtime. And the BigQuery sync within Dataflow allows the retrieval of failed inserts. Combining all these things together, we can actually achieve this dynamic mutating schema within our pipeline. If we were to look at our pipeline again, we may add in the get failed inserts when we're writing out to BigQuery. This allows us to retrieve everything that has failed insertion to BigQuery. Then we may invoke a function which dynamically mutates our schema. So everything that failed insert, inspect it, add the additional field to BigQuery, and then pass it downstream. And then finally, writing those mutated records out. Now, this allows us to do this fairly efficiently. So alternatively, what we could have done is we could have inspected every single message which enters our pipeline. And that's fairly inefficient because you're doing an operation on a bunch of elements that you may not need to. Right? This schema change may only happen occasionally. And so you're just adding overhead to your pipeline. So as opposed to doing that, reacting to the failed inserts, and then mutating the schema dynamically, and rewriting those records out to BigQuery allows us to have efficient dynamic mutating schemas within Dataflow. So if we were to look at our pipeline again, how does this look? We have messages that may have mutated schema. And essentially, we've added a whole new path here in which errors come out, and then we validate and we mutate that schema, and then we re-output it to BigQuery. And so without having to have this complexity of managing changes with our partners, we're able to react to it automatically within our pipeline. Another common use case is real-time denormalization. So in order to provide a summary view in our data warehouse, we may want to look up reference data before we output events. In our mobile gaming use case, this could be looking up reference data like on the user or on the partner, adding contextual information that will help us do our analysis later. In order to accomplish this, we'll need to add an additional data store to our architecture. In this case, we choose Bigtable because of the scalability and latency requirements that we may have. If our game is popular, we may be processing thousands, hundreds of thousands, or million events per second. So we need something that can scale to that. Before we implement the per record lookups, we want to consider both the performance of the database. So if we're doing this within GCP, we're going to prefer Bigtable or Datastore to do these per record lookups, because they'll give us the performance metrics that we need. If we were to reach out to BigQuery, it'd be quite a bit slower because you're talking on the orders of seconds as opposed to on the orders of tens of milliseconds for each individual lookup. And we also want something that's scalable too, because if we put, let's say, a single Postgres instance to do our lookups, Dataflow is like a cannon we shoot at GCP products, and so you can easily make a single instance fall over. So we want to keep that in mind when we're doing our per record lookups. And finally, we also want to utilize the right areas to initialize and tear down our connections. ParDos within Dataflow have a lifecycle, and I'll speak to that lifecycle in just a second. But essentially, we want to make sure that we're initializing and tearing down these connections in the proper place within our pipeline. So within the @setup method of the do function, and within the @teardown method of the do function to close the connection. So we're going to look at the ParDo lifecycle. This is sort of a crude representation of what it might look like. We have @setup, start bundle, and process element. And then we also have finish bundle and teardown. So where do we do our connection initialization and teardown? We're going to do that in setup and teardown, just like it sounds like. And the reason being is because it's executed once per dofun instance. So as these functions are distributed across your worker pool within your job, it's executed once, and so you don't have a ton of setup and teardown connections. It is rather expensive to create new connections and tear them down all the time. Start bundle and finish bundle are executed once per bundle of records. So within the pipeline, Dataflow will actually bundle records up and then process them to each transform. And this allows it to be more efficient and not have to materialize the output for each individual record. And we could have done it here, but this would be executed a lot more frequently because there's going to be a lot more bundles within the pipeline than there are instances of the dofun. So this would be a decent place to actually initialize and tear down our connections, but it would not provide the performance that we would like. And finally, we have the process element method, and this is executed once per worker. If you do really expensive things in the process element method, this is where you can slow down your pipeline. So for instance, initializing connections and tearing them down, if you're doing that for each individual record, and you're processing records at hundreds of thousands or millions per second, you are going to slow down your pipeline quite a bit. And so that's why it's pretty critical to connect and tear down your connections to do these external lookups in the correct place within your do fun. So zooming in on our pipeline again, we want to enrich data from an external store. And essentially, we just have added a couple different methods to the enrich messages do fun. Essentially, now we're in the @setup method. We're initializing that connection. We're calling a method to enrich the record, which will then call out to our external data store. And then in our teardown method, we're closing down that connection. And this allows us to have efficient per-record lookups within our pipeline. And then if we were to look at what our pipeline looks like as we add in this functionality, essentially, we have this additional lookup here, connecting to Bigtable, doing the per-record lookup, enriching the data with either user data or partner data for our game events, and then passing that data downstream. So now that we've done a lot of the common functionality that we may have to our pipeline, we may want to perform analysis on the data that's moving through. So this is where we may want to utilize some of the windowing techniques that I had mentioned earlier. So here we don't need to add any additional components to our architecture because windowing is handled within Dataflow itself. So there's nothing that needs to be added here. And for our analysis, as I alluded to earlier, we want to do some analysis to perform how long is a user spent playing a game. We may also want to possibly know when the user stopped playing. We may want to do things like, for a session, group together all the events and then compute and output one aggregate record that contains an array using BigQuery's nested and repeated fields to our advantage. And so here we'll actually do the, how long is a user spent playing a game. Now, if we were to use fixed windows, we inherently have problems because we may have family members that use the same device. And so if we were just to group by fixed windows of a period of time from like 12 to 1 or something like that, we may actually end up with different individual users within that time period. And so that would throw off our analysis of the count of messages that we're seeing per user, or even any additional analysis that we're doing on the user behavior. So this would have incorrect correlations. What we really want is to utilize the sessioning that I had mentioned earlier. Because with session windows, what we achieve is what we really want. We basically group together the events by a key, and that key being a user ID, for instance. And then we're able to get all the events for a particular user into one window, and then compute aggregations and do analysis on that window before passing that data downstream. And so this gives us exactly the subdivisions that we want. So looking at our pipeline code, we window the sessions with a gap of 5 minutes. So essentially, we are going to look at bursts of activity. And whenever we do not see activity for 5 minutes, we'll close that window and we'll fire it off. And that will trigger the aggregation downstream in our processing. After that, we're going to key by the user ID. So essentially, we're going to take that game event coming in, and then we're going to get the user ID. And this actually creates a key value pair that we can then group by. So essentially, we're keying these records before we group them so we can get the records into the right place. Then we're going to group by those records. So we're going to group by that key that we have with the game event. And that's basically going to create a grouping of a key to an array of all the records that map to that key within that session. And then finally, we're going to call a method or a class which is going to analyze our events. So within this class, we can do the counting or the averaging of those records. We can do the behavior analysis that we want to. And really, we can do any analysis that we see fit for our use case. So now looking at our updated pipeline, we have this whole new path. After converting to rows, we output to session windows, we key by the user, we group by the key, and then we analyze the events. And it all happens before we pass it downstream to BigQuery. So in this example, what we did is we deduplicated records using exactly once. We handled bad data. We handled mutating data. We handled enriching data in real time with these records. And then we also were able to then window these records into meaningful windows for our use case and compute analytics that we prefer. And so now I'm going to hand it over to Oliver to talk us through Dataflow at Sky.
Just to introduce myself, I'm Oliver Tweedy. I'm Director of Data Engineering at Sky. And for those of people who've not heard of Sky, we're one of the leading TV companies in Europe. We've got 22 million subscribers across the UK, Italy, Germany, and Austria, and we're a quad play provider. So we do TV, broadband, phone, and mobile services. And we selected Google in 2017 primarily for its data capabilities. So we spent about 4 months getting Google Cloud set up for Sky and designing our target architecture, and we've been up and running and live for 8 months now. So we consider GCP to be a great data and analytics platform as a service. So today I'm going to talk about Sky Q. Now Sky Q is our flagship TV platform. It's a TV box, and we think it offers one of the best TV experiences in the UK in terms of quality of the platform and the range of content available for the box. So Sky Q has a satellite tuner, it does video on demand, it does live streaming, it does HD and UHD content. And what we do is we collect diagnostic data from Sky Q boxes in every customer's home, and that's sort of 3 million boxes at the moment as live in the field. So we want to collect diagnostic data so we can understand user journeys. We want to be able to optimize those user journeys so our customers can find the TV content they love easily. So that means fewest clicks or shortest searches, easy to navigate UI, promotions and personalization. So for example, someone clicks on the home menu, they go to movies, they select a genre, they find the movie, they press play. So our original solution for Sky Q Analytics was based on a Hadoop cluster. It was a fixed size cluster on-prem. And Sky Q, great product, really successful, but the problem was that we had to deal with lots of peaks of data. So TV diagnostic data has large peaks. So in the UK, we don't have the weather of California, unfortunately. It rains a lot. When it rains, people go indoors, they watch more TV, they generate more diagnostic events. Also, we can have news events, we can have sports events, and on those days, we get more diagnostic events. So the problem with our fixed size system is that we have to over-provision. So effectively, if we're provisioning to the yellow line, we have a lot of capacity that's wasted. Whereas in worst case, we under-provision the system, and that means our batch processing or real-time jobs take longer, or worst case, we lose data altogether. The other problem that we had was that we spent a lot of time tuning our Hadoop cluster. I don't know how many people in the audience run Hadoop, but our ops team spent time tuning Yarn on a regular basis and dealing with managing Yarn containers. We had a platform with mixed workloads, so it's very difficult to get those workflows correct when things changed over time. So not a big surprise, we moved to GCP, and our architecture is designed around PubSub, Cloud Dataflow, and BigQuery. The reason is that we chose this is it's Google's canonical architecture, so really good integration between all those components. And we took the opportunity to move the pipeline from batch processing to streaming, because our modern Q boxes report back in real time over IP. And the other thing is that we chose to use Dataflow to gain the benefits of auto-scaling, serverless architecture, and out-of-order data processing. So much like Ryan's example with mobile gaming, people turn off our TV boxes at night. Quite often we get data turning up late. So out-of-order data processing is really important to us. So features in the Beam model, really important, and we also think the Beam model is becoming much more mature, and we like the sort of separation between the runner and the SDK. I think it's a good thing to be able to abstract the data pipeline itself from the infrastructure or the runner. So moving on to talk about our architecture. Effectively, what we do here is we take data in streaming mode in the ingest stage, so it's JSON data, just like in the mobile gaming example. We take it from our queue box into PubSub. Separately, we take reference data, batch mode into GCS. So then in our process stage, what we do is process this in Dataflow. So in streaming path, we clean the data, we add additional attributes, we assign join IDs, we sessionize the data, so session windows. We turn a sequence of user events into distinct TV sessions, and these are enriched with session IDs, start times, and the event number of sessions. So we think that the ability to dynamically add columns in BigQuery when our JSON schema changes is a great feature, and we make use of this. So this means we can have non-breaking changes with the source system. So our source system team just adds an element to the JSON message, and that manifests itself in BigQuery as a new column. So what we've got is also a separation between a first stage of processing and enrichment. And the reason that we do this is that we use our granular data for multiple use cases. And we don't always want to be able to use the enriched data in those separate use cases. So we have two stages of processing in our architecture. So in the enriched stage, what we do is we create this notion of queue box journeys. And these box journeys add things like the customer details, they add information around how the planner works and different reference data relating to the tiles on the UI. So for example, we can see then that somebody started searching for data on the box, they found Game of Thrones, and then they started watching Game of Thrones and engaged in a big Game of Thrones TV marathon. Finally, we display all this in Tableau, so we've got a number of aggregates that sit under Tableau and allow Tableau to perform effectively and give everyone really kind of snappy performance. So again, like in the example Ryan was talking about, we make use of sessioning for our TV events. So Sky process sessions based on a continuous stream of diagnostic events. Each one of those is calculated for an individual Sky queue box, and we do this based on a 4-hour gap of inactivity. So essentially what we're looking for is that 4-hour gap of inactivity, and then everything in that window before it becomes a session. We've got a hard cutoff after 24 hours on the basis that we think no one watches TV for more than 24 hours. So we also make use of auto-scaling. So auto-scaling happens transparently, but interestingly, the rules for auto-scaling are quite sophisticated. So don't expect auto-scaling to happen immediately when there's an influx of new work to do. Sometimes it takes a while for Dataflow to scale up, and that's because it's got a sophisticated heuristic in the background working and optimizing the number of workers in the Dataflow pipeline. So essentially, it might add workers to keep up with the input rate. So it knows the amount of unprocessed work in PubSub or the queue depth. And it might also need to catch up with the backlog. And it's smart enough to understand the rate of processing and whether it's worth scaling up those extra workers to process that backlog of work. So sometimes it might not scale up because it'll realize that by the time you've scaled up and added more workers, the work would be done. So what we've got now is a situation where we can process many hundreds of millions of records without having to manage any of the infrastructure and be able to cope with those peaks entirely dynamically. So we're regularly processing more than 300 million messages per day, in some cases now well over 400 million. It's been a great success in the business. It only took 5 weeks to develop this solution from end to end. And we agonized a bit about whether we should port our existing Apache Spark code over and run it on Dataproc. And we think we made the right decision not to do that and rewrite everything in Dataflow just because we've taken all the benefit of not having to manage the cluster. We also partnered with Datatonic, who may have in the audience, but Datatonic are experts in data engineering and machine learning, and they were able to get our team up to speed with Apache Beam, PubSub, BigQuery really quickly. We do A/B testing on the box software, so we can determine whether from one release of the Q software to the next that we're actually seeing material benefits and improvements in the software. So typically what we do is we take a small population of boxes, we roll those boxes up to the new revision, and we watch whether both old and new cohorts of box users are performing as we would expect, and whether the new cohort is seeing a material benefit. And in many cases, we can now find that we're seeing more than double-digit improvements in performance of the UI and user experience. So quick summary of before and after. So before we had an on-prem Hadoop cluster, we had to manage network, servers, software upgrades. We had to patch everything. We had a lot to maintain. Now we've got a completely serverless as a service model. We can scale in no time at all, like 90 seconds to add more workers, whereas before we were talking months to add new servers, where we may have to even put in a request to finance and deal with all of the capital expenditure outlay. So there's high fixed costs with the existing solution, and now we can just pay for what we use. One of the biggest improvements has been in development time. Before, with the fixed size system on-premise, it was almost impossible to recreate that production workload, especially with multiple workloads running on the same system. So development time took a long time because it was very difficult to test things and replicate the production workload. Now we can replay all our messages back into PubSub, through into Dataflow, and into the new developed version of our pipeline, and it's very much simpler to test, and that's meant that development now happening in weeks, not months. And ops are delighted. Rather than spending 2 days a week tuning Yarn, it's near zero ops. So again, great success for Sky, and also a great success for the business. So Dan Connell, who heads up our product experience, now feels that this is an extension of the product design and development capability. So he says, this capability has the power to change the way we develop our products and has made me very proud of what we've built together. And finally, I'd just like to say a couple of thank yous. So Datatonic, who partnered with us to build this, and also Agile Solutions, who helped do some of the project management. So thanks to Louis and Andrew on the technical side at Datatonic, and Stephen from Agile Solutions.